So in previous lecture, we have talked about the chapter 14, more on congruences. And in that we have defined the Fermat's little theorem. And Fermat's little theorem was given by French mathematician Fermat in 1640. The theorem states that let's say we have a prime number p and an integer a that is not divisible by p. Then we can write that a power p minus 1 is congruent to 1 mod p. And we have explained it by giving some examples. We have also proved this theorem. And then we have talked about some consequences of this Fermat little theorem. And then in the end, we have given this proposition which says that for two distant prime numbers p and q and an integer a that is not divisible by p or by q, then we can also write that a power p minus 1 multiply q minus 1 is congruent to 1 mod p into q. Now, to further talk about in this context, we are going to talk about the topic finding kth roots of kth roots modulo m. So, which means we are considering a congruence equation. So we consider congruence equation. Equations of the form that x power k is congruent to b mod m, where k, b, and m are integers, and we want to solve for x mod m. We can regard any such solution x as the kth root of b modulo m. So we can regard any such solution x is a kth root of b modulo m. So you can say, so solving this equation is equivalent to finding kth roots modulo m. Okay. Now, in fact, we now have enough theory in place to be able to do this under certain assumptions when m is either a prime or a product of two primes. So let's begin with an example. 14.1. We are saying solve the equation x power 11 congruent to 5 mod 47. Okay. Solution. So let x be a solution. So we can say x power 11 is congruent to 5 mod 47. It's the equation 14.2. Then we also know by Fermat's little theorem that we also know by Fermat's little theorem that x power 46 is 1 mod 47, and this is equation 14.3. Then this idea is to combine 14.2 and 14.3 in a clever way to find x. So the idea is to combine 14.2 and 14.3 in a clever way to find x. Now the key is to observe that 11 and 46 are coprime. And so using proposition 10.3 and exercise 10.3, we can find positive integers using proposition 10.3. We can find positive integers. You can find proposition 10.3 in chapter 10. Okay, so those are there in the lecture series. Positive integers s comma t such that such that 11s minus 46t is 1. So 11s is 1 plus 46t, and 11s is congruent to 1 mod 46. Then I hope you understand this. So we have just rewritten it, but like if you follow this, you can write this equation as 11s is congruent to 1 mod 46 from okay. Then by this calculation, we can write that x power x into x power 46 whole power t is equal to x power 1 plus 46t, and this is nothing but x power 11s, which is nothing but x power 11 power s. And so by 14.2 and 14.3, we can write this, that x is nothing but 5 power s mod 47, because this is x power 11 is congruent to, by 14.2, x power 11 is congruent to 5 mod 47. So if you can just replace that, and then we can write x is congruent to 5 power s mod 47. Okay. Now, in fact, using the Euclidean algorithm, we find that one is equal to 21.11 minus 5 into 46. So that is for that s is 21 and t is 5. So we take s is 21 and t is 5. Okay. Now, using the method of successive squares, that is example 13.3, we have been discussing before. We see that we see that 5 power 21 is congruent to 15 mod 47. Okay. Right. Then we can write, this shows that x mod 47 is 15 is the only possible solution. Let's say, to check that it really is a solution, work backward in the above equation. So if x is congruent to 5 power s mod 47, then x power 11 is congruent to 5 power 11s, which is congruent to 5 power 1 plus 46t. That is congruent to 5 into 5 power 46 whole power t, and that is congruent to, now we know that 5 power 46 is congruent to 1 mod 47. So that we can, from there we can write 5 mod 47, because 5 multiply 1 and 1 power t is just 1. So this is indeed a solution. So this is indeed a solution. So now we will talk about the general case by proposition. So this is a solution. Let's talk about the general case. So that is proposition 14.2. Let P be a prime and let K be a positive integer. Co-prime to P minus 1. Okay. Then 1. There is a positive integer S such that S into K is congruent to 1 mod P minus 1. 2. For any B as an integer not divisible by P, the congruence equation x power k is congruent to B mod P has a solution, has a unique solution for x modulo P. This solution is x is congruent to B power S mod P, where S is in 1. So we have a prime number and we have a positive integer k co-prime to P minus 1. There is a positive integer S such that we can write Sk is congruent to 1 mod P minus 1. Okay. Then for any B inside, for any integer b not divisible by p prime, the congruence equation x power k congruent to b mod p has a unique solution for x modulo p, and this solution is x is congruent to b power s mod p. We have defined this s in part 1. Okay, we can prove this proposition. So let's prove that. So number 1, since k and p minus 1 are co-prime, since, okay, proposition 10.3 implies that there are integers s comma t such that sk minus t into p minus 1 is 1. We wish to take s to be positive. Okay. We can do this by adding a multiple of p minus 1 to it. Provided we add the same multiple of k to it. K to t. So we are simply saying that we want to do s plus a into p minus 1 into k minus t plus ak into p minus 1 1 for any a. Okay. Now we now have sk is 1 plus t into p minus 1, which is congruent to 1 mod p minus 1 with s positive, proving 1. Okay. Number 2. Two says, suppose that X is a solution to x power k congruence p mod p, right? Since p does not divide b, does not divide x. So by Fermat's little theorem, we have x power p minus 1 is congruent to 1 mod p. Hence, x is congruent to x power 1 plus t into p minus 1, which is congruent to x power sk, which is congruent to x power k power s, which is congruent to b power s mod p. Perfect. Hence, the only possible solution is x is congruent to b power s mod p, and this is indeed a solution. This is indeed a solution, since b power x power k is congruent to b power s into k, which is congruent to b power 1 plus s 1 plus t into p minus 1, which is congruent to b into b power p minus 1 power t, and this is b power p minus 1 is congruent to 1 mod p, so this is just p mod p, which proves the theorem. Perfect. So this is our proposition with the proof. Okay. Perfect. Now, a simple modification of the proof enable us to find the k power kth roots modulo a product of 2 primes. And here is the result which will be crucial to our discussion of secret codes in the next chapter. So let's give another result for the product of 2 primes. Position 14.3. Let P comma Q be distant primes. And let K be a positive integer co-prime to P minus 1 into Q minus 1. Then 1, there is a positive integer. There is a positive integer s such that sk is congruent to 1 mod p minus 1 and q minus 1, and two is for any integer b not divisible by p or by q, the congruence equation x power k mod b congruent to b mod pq has a unique solution for x modulo pq. This solution is x congruent to b power s mod pq, where s is in in 1. Okay, nothing different, just we are considering the two primes and then their product. Everything is quite similar. So the proof is going to be same the proof is just like that of the proposition that of the previous proposition, except that at the beginning we find integers s comma t such that sk minus t into p minus 1 q minus 1 is 1. And it the and we use proposition 14.1, previous one, instead of Fermat's little theorem. Okay. And then we will prove this proposition. Okay, perfect. We'll end this part of the lecture here.